Thank you. So, the subject of my presentation is digital sorting. And what I really would like to do is, first of all, first start the presentation would be nice. There we go. Okay. Good. So I want to really give a primer on digital sort technology, what it is, how it works, and then speak specifically about application examples and the role that this technology has in vegetable production operations to make sure that product is delivered to consumers, to your customers that corresponds to their quality expectations, and that objective is achieved at the maximum possible process yield, which in turn translates into a profitable vegetable producing operation. So first of all, what is digital sort technology? Digital sorters are sensor-based equipment that automatically performs the intelligent selection of product based on user-defined standards, based on what is your definition of quality with respect to your product. And they automatically select product that corresponds to those criteria, and they separate out of the product stream product that is not compliant, as well as foreign materials and other contaminants that invariably find their place into the product stream whenever we're talking about food production or vegetable production in this case. This function has been traditionally performed manually by human inspectors, and really the technology as it has evolved is finding its space increasingly in vegetable production operations due to a couple of fundamental advantages. One is the ability of the technology to perform a very consistent inspection reliably, including in some cases the ability of sensor technology to detect internal defects and other product characteristics that are not observable on the outside of the food object or the food product. And then, of course, the other big driver for the propagation of this technology is the fact that manual labor in many vegetable production settings is becoming increasingly expensive, or in some cases, regardless of cost, increasingly difficult to procure, train, and retain through the course of the season. But the payback, therefore, on the investment in this technology is usually realized by vegetable growers in terms of more consistent quality for their products, reduction in labor cost, but also in the ability to leverage the sorter as an information center for their production operation. The digital sorter will see literally every single item that is going to go through your facility, through your operation, and is able to collect and catalog information beyond what is necessary to physically perform the sort. This information, such as quality trends and their evolution as you're processing, for example, product from different fields or from different suppliers, helps users of this technology optimize their operation and make production decisions to improve their process yield. So let's talk briefly about how a digital sorter works. The digital sorter typically guides and directs a flow of product into one or multiple inspection zones where sensors are configured depending on the characteristics of the product that is being inspected. Different types of sensors are optimal for inspecting different types of product characteristics, and we'll see that in a second, and I'll talk a little bit about the different types of technologies that are employed in the process. Once their sensors have inspected the product stream. And by that I mean they have inspected literally each individual object in the product stream. Their input is transferred over to what we call a sort engine, which is the computer where the software algorithms reside that are going to be making the decision of whether each individual object in the stream is in fact compliant with the quality characteristics that you have defined in the sort recipe, or whether it should be removed from the product stream because it does not comply with those requirements, or because in fact it's not even a product item itself, but it's a foreign material or a contaminant. And the physical separation of bad from good is achieved mechanically in a couple different ways. Depending on the size of the object, we either have mechanical deflectors or we have air nozzles that precisely puff at the offending object, at the item that we want to remove from the product stream. They alter its trajectory, and then they cause it to land in a different physical zone than the good product. So that following the sort process, you have a collection area for good product, for compliant product that can go on to packaging. And then you have an area where defective product and foreign materials are collected. It's also possible for this equipment to separate the product stream into not just 2, but also 3 different streams. And for example, an application of that would be a situation where you have, for example, one stream being dedicated to trash and foreign material, and then the other 2 streams are used to separate good products of different grades. Because obviously in many vegetable production operations, your definition of quality product can be flexible. You may be producing one day, let's say, a grade A product with very, very tight tolerances with regard to the presence of defects, of any defects on the product. And you may have also, in some cases, let's say, a second grade product that is doesn't make the cut for grade A, but it's still sellable or it's something you can utilize in a different way. Another example would be we have, for example, let's say a green bean processing operation where the sorter deposits in one collection stream trash and foreign materials. Good product is allowed to go through. And then in a third collection stream are green beans that are actually good quality, but they have stem or stalk attached to it. Those beans are sent a separate way. They're reprocessed for separating the stem and stalk, and then now they become good beans, and they can join the rest of the good beans to go into packaging. Let me speak a little bit about the type of technology that resides inside of the machine. So how are we able to make such sophisticated decisions about the quality of the objects that we see going through the machine? Each product can be inspected across a number of different quality criteria. Color variations. Color variations sometimes represent defects in certain vegetable products. The integrity of a product, for example, if a green bean, to stick with that example, is whole or broken. In some cases, the shape of the product, excessive curvature can be considered a defect by a retailer, everything else being equal. And so we also have machines that have shape algorithms that can help determine whether the shape of a product is compliant with the quality definition of correct shape. And we can also distinguish products based on their structural characteristics. So each of those selection decisions can be achieved through a range of different sensors that are matched to the characteristics of the sort that is being performed. We use, in some cases, uniquely or in combination sensors such as high resolution, multi-channel digital cameras. Those sort of sensors are typically very, very good at detecting color variations. We also use digital laser scanners. Laser scanners are not as good as cameras at detecting color variations, but superior when it comes to detecting structural differences in the material that is being inspected. We can combine those two different sensors, and also a new type of sensor technology that is finding increased applications in digital sorting of food products are hyperspectral imagers. Those imagers are capable of performing near-infrared spectroscopy, and in fact, in some applications, those images are capable of detecting internal rot and other defects and product characteristics that are internal to a vegetable product, and therefore could not be discerned by a machine or a human simply by looking at the outer surface of the product itself. So this is very sophisticated technology, increasingly capable, and I also like to speak when I talk about this about the challenge that we have as developers of this technology to make sure that all of this capability, but also all of this technology complexity and sophistication stays inside the machine. We cannot develop even the most capable machine in the world if then it is going to be requiring an engineer or a PhD to operate. The value and the evolution of this technology that I find remarkable is the fact that as the machines grow more and more capable, paradoxically, they also grow easier to use. And developers of technology like Key Technology, which is a company I represent, spend a lot of time worrying not just about the detection capabilities of the system, but also in making sure that the human-machine interfaces are very simple so that a minimally trained operator with only basic computing skills is able to get up to speed and operate the machine to the full extent of its capability within a couple hours of training. So in summary, the benefit of digital sort automation are the ability of those systems to make in milliseconds very, very complex quality assessment decisions that would be impossible for a human or even a team of human inspectors to make reliably, consistently over time. The ability to identify very fine defects when that is needed, or indeed even defects that are not immediately discernible by the human eye or by other sensor types by inspecting only the outer surface of the object. There are obviously significant efficiencies in labor savings that go on from implementing this technology in vegetable production operations, and also again the ability of the sorter to serve as a true information center for your production operations. And we have several examples of integration of our technology with factory automation systems. Examples where, for example, vegetable producers who, in addition to growing their own product, procure product from third parties using reports from digital sorters to regulate payments to their suppliers depending on the quality of the raw product that they have received. So let's look at some examples of product applications for digital sorting in automatic selection of products. And here I am using, obviously given this audience, I'm using examples that are relative to minimally processed and fresh cut vegetable products. The same type of technology find application also in other food production environments for processed vegetable, fruits, nuts, dried fruit, seeds, grains, etc. I'm going to sort of try to use an example here to illustrate and make everything that I've talked about, the description that I've made of this product technology more real by looking at a specific application case. So in this case, we're looking at a producer of organic fresh cut leafy greens. This is a company that produces salad mixes as well as packaged fresh spinach. And their objective in considering an investment in digital sort technology was the ability to tighten down even further the elimination of foreign materials from the product and contaminants. The ability also to make flexibly quality decisions about the product itself. So, for example, they're selling to certain retailers that are more sensitive than others to color defects on the leaves themselves, yellowing, dark defects. And as they have different customers, different retailers that have different levels of tolerance for those defects, they want to have the ability to manage the sort around those defects so that they maximize their yield. They're delivering to the customer exactly the quality they expect at the maximum possible process yield for themselves. And in the case of this customer also, there was an important consideration with regard to labor. Not just the cost of it, but in this case, this customer, which is located in the United States in this example, was just increasingly unable to find people that would come to work as inspecting their production lines, training them, and then also retaining them through the season. And so in this case, it was more labor availability, even more so than labor cost, in terms of their desire to automate the process. The next couple slides I will show as kind of an example of how, as a supplier of this technology, we engage the customer to design and develop a system around the specific sort requirements for their product. We obviously understand the conditions of the product, the characteristics of the product. There is an element also of sizing those systems so that they are a match for the throughput requirements of the customer operation. And then, of course, the critical aspect is understanding the foreign materials and the type of product defects that are of interest to the customer, to the vegetable producer to manage through the sort process. And here we have kind of a list of a number of organic and inorganic foreign materials that are of particular concern to this customer operation. And also at the bottom, as I mentioned earlier, there are some quality, color-based, color-related defects that relate to the leafy product itself. So based on that understanding of the sort requirement, we configured a specific arrangement for one of our sorters, inspecting the product flow both from the top with cameras and laser scanners, as well as from the bottom. And in this case, inspecting the product from the bottom gives us the best chance to really identify product defects and foreign materials wherever they may occur. If we have a tendency, for example, for some heavy foreign material contaminants like animal parts or insects, which are very typical in leafy greens, to reside sort of on the underside of the leaf. And if that's the case and we inspect the product only from the top down, then we would run the risk of missing those defects that are hidden by the product itself. Inspecting the product from both sides gives us maximum sort of removal ability for defects wherever they may occur on the product. So if you're curious to see what all of this looks like to the eyes of the system, to one of the sensors, here's an image that is taken from one of our digital laser scanners. In this case, we are utilizing the scanner to inspect in a frequency range where the chlorophyll that is contained in the leaf of the product is reflecting, and that reflectance allows the scanner to differentiate very, very clearly between good product, which is the green leaves that you see there, and then everything else that is not good product appears distinctly dark and different from the good product image, and therefore is possible for the system to make a very, very clear discrimination as to what they're looking at. To give you an example of why we're discriminating based on structure in this case, when you look at, for example, the rubbers and plastic, you see there objects that have irregular shapes that could look shape-wise like a leaf. And let's say that you have maybe some pieces of plastic or paper that find their way into the product stream that look like a leaf, and maybe they even have a color that's very similar to the leaf. If we were to try to segregate for a material only based on color or shape, we would be missing some of those. But being able to look at the structural properties of the material that we're looking at makes it very clear for the sensor to see what is good product versus what is an organic or inorganic contaminant. And then just for fun, I included on the sort of lower right-hand side the image of a scanner that is on a system that is inspecting green beans. And you can see here a little frog that found its way from the field all the way into the packaging facility, and that the system has obviously quite clearly spotted and identified the unwelcome guest. Let me jump ahead to another sensor image, and then I'll come back. This is a camera that is imaging green beans. And in this case, we're using a camera as opposed to a laser because the camera is better able to resolve color differences that can be present on the bean itself, as symptomatic of damages, rot. But also the camera, in combination with the software, is able to make a very intelligent decision, in this case, about what beans have a stem or stalk attached to them. So in the case of this particular customer, they wanted to remove beans that had an especially long stem or stalk remaining attached to them. And as you can see, using shape algorithms, the software is able to profile and to identify exactly where those beans are. And again, think about the fact that in a flow of beans, as much as 15 metric tons per hour going through the machine, we're able to perform this level of inspection of each individual object within the product stream, and then pick out only those beans that have this defect. In this case, the rest of the bean is good product, so those beans are not going to get thrown out. They're going to be reclaimed so that they can be go back to get snipped and for the stem and stalk to be removed, and then they could go on to packaging so that the customer is looking to maximize their yield and not throw away any good product in the process. I wanted to show here what this looks like in practice, and going back now to a leafy green application example. Here's a digital sorter that is processing chopped romaine, looking for remaining core that needs to be eliminated, as well as leaf defects. So as you can see here, the product is being inspected, and you'll see it in a second being launched in the air, and you will see how the ejectors that are located on top of the product stream are puffing from time to time and causing defects and remaining core to be diverted and to fall down to the bottom. And what's left is, on the other side, the accept stream, which features a clean product ready to go on to be packaged. And then the reject stream contains remaining pieces of core and leaves with yellowing and other defects. Here's the same machine now processing, in this case, iceberg lettuce, shredded. It performs the same type of sort. You can see here again even more clearly how FM and product defects are being deflected to fall down to the bottom, and only good product is allowed to go on and pass through. And as a result of that selection, then at the end of the process, you are left with a very, very clean stream of good product. And contaminants, residual pieces of core, and other foreign material is separated from the product stream. So I won't go in detail through this. I wanted to put together, and I think you'll be able to obtain this presentation if you're interested through OSVEG, but I wanted to put together just a little bit of a primer here on things to think about in considering the adoption of this technology for your particular vegetable production operation. And of course, if you should have specific questions regarding the application of this technology to your particular product, to your particular production situation, I'm certainly happy to speak with you afterwards. We'll have a little bit of Q&A, and I'll probably see some of you the rest of the week. We also, I come from the US. I'm actually Italian originally, working and living in the US at the moment. We have an Australian operation for the company I represent, Key Technology, including a demonstration lab and a test lab. And those of you who are interested are also certainly welcome to make contact with our local representatives. So thanks very much. I hope this has been kind of an informative primer on the wondrous capabilities of digital sort technology, and also how we expect to continue to evolve it to add more value to vegetable processing operations. And enjoy the rest of the conference.